Hi everyone, I'm Raghav and today we'll be talking about coroutines and Go. So, a little bit about myself. I'm a software engineer at VMware. I work with the ESXi hypervisor. When I'm using Go, is generally on my personal projects or when I'm contributing to open source, something like Kubernetes maybe. So, just to set the expectations of the talk a little bit, we're going to be covering coroutines as generalized subroutines. So a little bit of we'll cover a little bit of basics over there, how it all started, where and how coroutines came to be, classifying coroutines, and why the concept of full coroutines is important, and how some languages actually don't provide full coroutines. Implementing coroutines in Go using just pure Go definitions and Go semantics. And finally, some Go runtime changes that could be made to support coroutines natively and far more efficiently. So to begin with, brushing up on some basics, what are subroutines? Subroutines are essentially your regular function calls can do certain things. They can suspend themselves and run another function, or they could terminate themselves and yield back control to its caller. These are the two things that your functions can do, right? So in this case, say you have a main subroutine, suspends itself, starts another function. This function can execute, and as soon as it has to call another function, it can suspend itself, call this third function, which can, start functioning again. After this outermost function has, finished processing, it can terminate, yield back control to its parent caller, which can terminate again and yield back control to its parent. So this is what a regular subroutine looks like. So now subroutines, now these definitions differ depending on where you are looking on the internet. But for this talk, eager and closed means that, well, eager means expressions that a function encounters are evaluated as soon as they are encountered, and closed means that your function only returns after it has evaluated the expression. So it can't sort of suspend itself in the middle of processing and yield control back to its invoker. That's the important difference that we'll see soon with coroutines. Now, coroutines as generalized subroutines, can we define them as generalized subroutines? And what I mean by that is a coroutine can do everything a subroutine can, which means it can suspend itself and run another function, terminate itself, yield back control to its invoker, or this magic special thing at the end, which is suspend itself and yield back control to its invoker. Instead of, so it just passes the control back to its invoker, pausing itself essentially. So how could that look like? Say you have a subroutine running over here and you want to run this coroutine on the left. So your subroutine suspends itself and say it wants to read from some output that is output from this coroutine. So your coroutine starts functioning. After it has the output, it can suspend itself and yield control back to your subroutine with the output. And now you can see that the coroutine is actually stopped here. It has saved the state and it's actually paused in the middle of its execution. The next time the subroutine wants to read from it, it actually can just resume this coroutine, which starts running from its previously stopped position and output the new value that the subroutine requires, which can be read by the subroutine, and so on and so forth. So it ends up looking like this. Every time this subroutine wants to read from a coroutine, it plays this coroutine back, which starts executing again from the last time it stopped. Now you will start seeing why this is important, and you can probably already start seeing why a paradigm like this could be pretty useful. So coroutines are like functions that can return multiple times and keep their state, which means all the local variables plus the command pointer, everything, and they can resume from where they are yielded. So let's look at a pretty quick example, right? So comparing binary trees. Those in the audience who like doing lead code, if you've seen something like seen a question like this, right? How would you do this? You would have some sort of a recursive logic. You have two binary trees and you want to compare them and maybe ascertain if they are equal. So you would go through all the nodes, save in maybe like an in-order fashion, and save all the values of the nodes. And after you have traversed both the trees, you compare those values. So, but what if you could actually do this in one pass? Say, have every time you're at a node, you can pass through both these trees, compare the values of the current node, go to the next node in the next node say in order fashion, and just keep comparing the values as you go through them. something like we just saw in our subroutine and coroutine example. Let's see that with code, right? So in this case, your subroutine is this CMP, this comparison function, and your coroutine is this visit function. And how this is working over here is your comparison function is just instantiating two coroutines. We don't need to worry about how they're implemented. Just assume they're just black box implementations. It creates a new coroutine, in this case, the visit function. So you're passing this visit as a function argument. And in this while loop, all you're doing is you first start your first coroutine, your CO1, and you're passing T1, which could be this head of the first tree, and your T2 is probably the head of the second tree, right? So you resume this visit function. So your visit first goes to T left, so it goes all the way to the leftmost node in your tree, your leftmost node in your leftmost subtree, and it then yields the value back to your back to your resume function. So the next line yield actually yields back control to your comparison function, and this value is stored in V1. Now this comparison function then calls CO2, which is another instance of your visit function, and you pass T2 to it, and it goes through that tree and gets the leftmost node in this case, which is 2. And now you have both the values actually yielded back to V1 and V2 that you can then compare. So essentially, you have you start traversing the tree in sort of a one pass sort of a way. You're just passing back control to visit, and as soon as it has an output, you're reading the visit function yields back control to your comparison function, and you can do your comparisons. So again, in the while loop, you call your resume function again. It goes to the right subtree from 2, which is 4 in this case, for both the trees, because it resumes both the coroutines one by one. It yields back the values, and now you can compare 4, so on and so forth till you know both the trees are same in this case. This is actually this sort of an example was actually why coroutines came in the first place, or why Conway thought of them. It's 1958, and you want to compile your COBOL program in the modern 9-path COBOL compiler. That's Grace Hopper, by the way, who is the co-developer of COBOL. Now the terms over here, even if you don't understand it, I'll simplify it. So you just your basic symbol reducer, you can think of it as your lexer. And if you don't know what a lexer means, that's fine too, because all you need to care about over here is that you have two processes, like you had in your binary tree comparison example, that sort of depend on each other for their outputs. So in this case, your basic symbol reducer acts like a lexer. So what your main program does is that it has actual physical punched cards. That's how compilation worked back in 1958. And you give this punched card to your basic symbol reducer, or your lexer, which eats this punched card and spews a bunch of tokens. Now the tokens is what the output of your symbol reducer is, or your lexer is, right? Now these tokens can be read by a parser, these tokens become the input to your parser. In this case, your basic name reducer, or name lookup as it's called today, which puts the output into the next state. So what's happening over here is sort of like our first subroutine example. Your main program, your control goes to your basic symbol reducer, which comes up with a bunch of tokens as outputs, and it returns essentially these outputs back to your main program, which can then your main program then calls your name reducer with your output of the basic symbol reducer as an input to your name reducer, and your name reducer can then start parsing your tokens. So this is kind of what it looks like. Initially, what we saw, your main program calls symbol reducer. Symbol reducer writes a bunch of tapes to your, and these tapes are basically used as input to your name reducer. You have a bunch of extra tapes that you don't need anymore, and this entire process actually involved a bunch of extra machinery, right? So Conway thought there had to be a better way to pass the input that you get, pass the output that you get from your symbol reducer or your lexer to your parser, which is your name lookup, without all this expensive machinery. And we'll start to see how he actually thought of the coroutine. And he realized that subroutines, which was the previous implementation, were just a special case of a more generalized coroutine, the first thing that we saw in this talk. And we don't need to write on tape. We can just pass control back and forth between these two processes, because the input of one process is the output of the previous process. So you don't have to return, you can just yield back control. and you bypass all this machinery, and this is how it ends up looking, which is very similar to our previous example. So every time your name reducer, your parser, wants to read a token from your lexer or your symbol reducer, it invokes this coroutine, suspends itself, and as soon as your symbol reducer has the tokens available, suspends itself, yields control along with the output to your name reducer, which is your parser, which can do whatever it wants with the output. And when it wants the next token, it again resumes your coroutine, and which yields back another token, so on and so forth, till you reach the end of your main function, right? So this way, raising the level of abstraction actually led to less costly control structures, leading to a one-pass COBOL compiler. So this was an example of a negative cost abstraction, because generally when you're trying to abstract away logic, you're increasing the cost because something else is now taking care of this easier abstraction that you've created, something under the hood, right? So this side note, this was the paper that actually coined the term coroutine by Melvin Conway. I've linked to this paper at the end of the talk, and you should definitely check it out. Where are coroutines now? Considering all that we've talked about so far, coroutines should have been a common pattern that is provided by most languages, right? Seems pretty useful. But with a few rare exceptions like similar, few languages do. And those that do, and I'm guessing some of you already have some ideas of, some other languages calling their processes coroutines. They are actually a limited variant of a coroutine, and we'll see what makes them limited and why we want why this could actually affect the expressive power of a coroutine. So the problems with coroutines were also apart from the reason why we don't see it everywhere is, one, there's a lack of uniform view of this concept. There aren't a lot of formal definitions that people agree on what coroutines means. So there's no precise definitions for it. And secondly, more importantly, why coroutines aren't provided as a facility in most mainstream languages is the advent of Algol 60. So this language brought with it block scope variables. So you no longer had parameters and return values stored as global memory. Instead, everything was stored as relative to a stack pointer. So your functions are stored on a stack as stack frames, right? So with the return addresses, all your local variables, everything is on a stack now. You have your stack, you have F's activation record. So your F is a function, and its activation record just contains all its local variables, return addresses, and a stack pointer is just pointing at the top of the stack. Your function can call a more function. In this case, it calls function G, which has its own activation record, which can call function H, and so on. So how would you try to implement a coroutine in this sort of a paradigm? Well, you could have your F, in this case, wants to call a coroutine G. You could have G running as a separate stack on the side of this thread 1 stack, right? As a side stack. And your stack pointer now has to move from one stack to another stack with all the thread context, your return addresses, saved registers, everything has to move to this stack now, and which calls the function G, which is a coroutine. Coroutine G can call more coroutines H, right? Now, what if there is another function, not F, but some other function that's interested in the outputs that these coroutines are producing? Well, you can think of it as second stack. You have a thread 2 stack. This is different from F's stack, and you have some function Z that's running over here with the stack pointer now. When the control comes to Z, the stack pointer has to move over here into the second stack with all the thread context and everything else. So this almost starts mimicking heavy multi-threading, which increases the memory footprint rather than the cheap abstraction that coroutines were meant to be in our previous examples, right? What about the precise definition problem? Well, Marlin's doctoral thesis is actually widely acknowledged as a reference for this, and it just summarizes whatever we have discussed so far, which is the values local to a coroutine persist between successive calls. It can pause itself and save the state there, and the execution of a coroutine is suspended as control leaves it, only to carry on from where it left off when control re-enters it. So when a coroutine yields, the control leaves it where it left, where it yielded, and when you resume a coroutine, it starts processing from where it had stopped. Basically what we've already discussed. So now that we have the basics and the history out of the way, and hopefully have made a case for its usefulness, let's build up to what a coroutine looks like in Go. But before that, very quickly, I promise this is relevant. Uh, let's look at what we mean by a full coroutine. And some languages like Python and Kotlin, which actually provide coroutines, don't actually provide full coroutines. So let's start, just for the sake of completeness, let's start classifying your coroutines. Well, one kind of classification is symmetric coroutines, which is different from what we've been seeing so far. A symmetric coroutine only has one control transfer operation, and so it disallows coroutines to explicitly pass control amongst themselves. But what we're interested in is asymmetric coroutine mechanisms that provides two control transfer operations. In our case, it was the resume and yield operation. So one for invoking the coroutine, your resume, and one for suspending it, the yield, and the latter returns the control to the invoker. So coroutine mechanisms that support concurrent programming usually provide symmetric coroutines. On the other hand, coroutine mechanisms intended for producing sequences of values are provided by asymmetric coroutines. And you might think, wait, then why not just use symmetric coroutines? It seems like it's doing way more important things. Concurrent programming is what Go is all about. But actually, the good news is that you can use asymmetric coroutines to mimic symmetric coroutines. And asymmetric coroutines are way easier to write and maintain. And actually, I have linked an article to the end of this slide to actually you can see how symmetric coroutines and asymmetric coroutines are implemented, and how you can actually implement symmetric coroutines using asymmetric coroutines using your resume and yield functions. So, but with the advantage of that, it's easier to write asymmetric coroutines, and we'll see that when we implement our Go API, we implement asymmetric coroutines. Secondly, you would want your coroutine to be provided as first-class objects by your program or your language. It has a huge influence on its expressive power. And coroutines that are constrained within the language bounds cannot be directly manipulated by the programmer actually has a negative effect on its expressive power. So what do we mean by a first-class object? Something we've already seen with the binary comparison example. Your coroutine should be able to appear in an expression. You should be able to assign it to a variable. You should be able to use it as an argument, return it by a function call, all the good stuff. Finally, stackfulness. This is the important one. And this is what actually differentiates Python and Kotlin's coroutines, or most of the languages, from a full coroutine, is because when you have stackful coroutines, you can actually transfer control between nested functions. So even if your coroutine isn't at the topmost stack, even if your coroutine is somewhere in the middle of the stack, you can still yield control from the coroutine back to its invoker. When you have stackless coroutines like Python and Kotlin, they are in full coroutines, and the only way you can pass control between two coroutines, or a coroutine or a subroutine is by sort of only the topmost coroutine and the topmost subroutine can pass control between themselves, which actually limits what your coroutine can do. Basically, your full coroutine should be stackful, should be provided as first-class objects, and we can implement them using asymmetric coroutines. So full coroutines can be used to implement generators, iterators, all the way up to cooperative multitasking. And just by providing asymmetric coroutine mechanisms, it's sufficient because we can use it to implement symmetric coroutines, and asymmetric coroutines are just much easier to maintain and implement. This is a nice way to show the limitations of a coroutine. So cooperative multitasking, right? In a cooperative multitasking environment, your concurrent tasks are interleaved. So one task runs and stops itself, the second task runs. So this interleaving and this it needs to be deterministic. But when you're using coroutines, coroutines by definition are non-preemptive. So there's a fairness problem that can arise if you have a bunch of coroutines running in your kernel space. So because your kernel space doesn't have just one program that's trying to operate, that's collaborating amongst itself. It's actually a bunch of programs running that could be waiting for the CPU resources. Now, if a coroutine is using a CPU resource, that maybe the coroutine panics or it hangs or just taking a long time to execute, a higher priority task could be waiting for this coroutine to finish executing. Right? This sort of fairness problem can arise because of coroutines being non-preemptive. So, but on the other hand, if you have user level multitasking, implementation, your coroutines are generally going to be part of the same program that is collaborating to achieve a common goal. So since you can still have fairness problems, but since it's restricted to your one collaborative environment, it's much more easy to identify them, reproduce them, and makes it less difficult to implement. So this you start to see why full-blown coroutines in your, in kernel space, for example, might not be a good idea. Why coroutines in Go? Coroutines aren't natively served in Go concurrency libraries. And this was an interesting talk by Rob Pike, actually, lexical scanning in Go. I won't go into the definitions, but I've linked to the talk. What they did was, for their implementation, they used Go routines connected by a channel. Now, full Go routines provided to be a bit too much because Go routines provide a lot of parallelism, right? So the parallelism that comes with Go routines caused a lot of races. Proper coroutines, as we'll see, would have avoided the races and would have been way more efficient than Go routines because of their concurrency constructs. Only one coroutine can be running at a time. Now, coroutines, threads, generators, they sort of start sounding the same. So let's get the definitions out of the way a little bit. Coroutines provide concurrency without parallelism. That's the big idea here. When one coroutine is running, the others aren't. Threads, on the other hand, are definitely way more powerful than coroutines, but with more cost. They require more memory, more CPU allocation, and also it comes with parallelism. So you have the cost of scheduling these tasks, and you have way more expensive context switches, and the fact that you need to add preemption for threads. Go routines are like threads, they're just cheaper, so they use lesser memory, and all the scheduling is now taken care of Go's own user space, Go scheduler. So your Go routine switch is closer to a few hundred nanoseconds, which is way faster than a thread. Generators are like coroutines, but they're stacked less. They're not stacked full. So you have the problem that we discussed. They can only transfer control between the topmost stack frames between two threads, for example. So with all this in mind, let's start building an API for coroutines in Go by using existing Go definitions that's available today. And this next part of the talk is heavily borrowed from Russell's research proposal, which I've linked to at the end of the slides for implementing coroutines. And check that out because I've skipped a lot of the information here. So it's very neat that we can do this using existing Go definitions, your coroutines, channels, the fact that Go supports function values, the fact that unbuffered channels can act like blocking mechanisms between coroutines. So it makes it coroutine safe. A coroutine can do a bunch of things. It can suspend itself, run another function, a coroutine, terminate itself, yield back control, or suspend itself. It doesn't need to terminate itself. It can just suspend itself to yield back control. So let's start with a simple implementation of the package Coro. So in this case, you have a caller and the callee, and right now we're looking at the suspend and run scenario. So you have a caller, which, so now this can be two Go routines that are say connected by a channel. Your coroutine, which is your callee, could be waiting to receive from C in. Let's call the first channel C in. So if your caller or your subroutine wants to resume your coroutine or your callee, all it needs to do is write into C in. So as soon as it writes into C in, your callee starts running. And now you need a way for your caller to sort of stop executing as soon as it resumes the function. So what it can do is it can wait on another channel. It can block itself on, say, C out. So as soon as it resumes a coroutine, writes into C in, which your coroutine was blocked on, your caller can be blocked on C out. So as soon as your callee or your coroutine stops executing, it's finished executing, it can write into C out. And it block itself on C in again. So your coroutine is blocked, and you have now successfully resumed your caller or your subroutine. So this sort of we're already starting to see like a control transfer mechanism come into play. Your new function over here, this function new in your package Coro, all it's doing is it's instantiating two unbuffered channels, your C in and your C out. Your resume function. Okay, let's look at the Go function first. Your Go function, this coroutine, is essentially what your coroutine with a C, right? So you can see that your function that this Go function is running is blocked on C in. When you want to resume this function, you call this resume function. All it does is writes into C in and waits on C out. And as soon as your Go routine finishes executing your function F, it writes the output into C out which unblocks this resume function, and your go function can be blocked on cin again, right? So you can pause and see how this works. So the new go routine blocks on cin. So so far you have no parallelism because only one function, one routine has the control. Now let's add the definition of yield that we've been talking about so far, and basically return its value to the coroutine that resumed it, right? So right now we're looking at suspend and yield. So your yield is just the inversion of your resume. So in your yield function, you're writing into cout, and when you write into cout, you wait to receive from cin. So your coroutine is writing into cout, which your subroutine is blocked on, and as soon as you do that, you're blocked on your coroutine is blocked on cin. Your caller starts functioning, and once it wants to resume the function again, it can write to cin again. So that's great. Now you have now if you notice, it's just the inverse of your resume function. It writes into cout and blocks itself on cin, and you can actually pass this function in your Go routine. So that is great that Go allows you to pass function values in other functions. So as callback functions. So on a note, you have only added another send receive pair, and there's still no parallelism that's happening, right? So that's the whole point of coroutines. So let's pause for a bit. Are these actually coroutines? They're still full Go routines, and they can do everything that an ordinary Go routine can. Your coroutine, your coro new, just creates Go routines with access to resume and yield operations. Unlike the Go statement, we are adding new concurrency to the program without parallelism, right? So if you have Go statements in your main function, say you have 10 Go statements in your main function, now you have 11 Go routines running, and they can be running at once. So your parallelism is actually gone up to 11. But if you have one main Go routine that runs 10 new Coro new calls, then there are 11 control flows, but the parallelism of the program is still what it was before, just one, right? So Go creates new concurrent parallel control flows, whereas your Coro new, which is the implementation that we're developing, creates new concurrent non-parallel control flows. So let's get back to implementing our Coro API. It was pretty crude, and we can start improving it a little bit. So first, what if your callee or your coroutine wants to terminate? Instead of yielding back control, it wants to just stop executing. So say your coroutine stopped executing. How does your caller know that it stopped executing, right? It can try to resume this coroutine that does not exist anymore, and block itself on cout, but there is nothing to write into cout because your coroutine does not exist anymore. So a simple solution to this could be just have a global variable called running, and as soon as your coroutine stops functioning, just set running to false. All your caller needs to do is before it resumes this coroutine, just ask, is this coroutine still running? If not, don't try to resume this function. Now you might think that having a global variable when you could have potentially a bunch of coroutines that are running, a place for data races. But if you recall, you can have only one coroutine running at a time. So this sort of sequential, consistent, execution ensures that there are no data races happening at this running variable. So a very simple implementation over here. You have this running variable, and you should set to true. As soon as your go routine, which is your coroutine in this case, executes this function f, your running can be set to false. And the next time you want to start this function again, you check, is running set to false? If it is set to false, then just return. If it is not, write into cin, resume that function, and so on and so forth. Another thing is that, sure, if it terminates properly, then you have your running properly set to false. But what if your coroutine actually panics, never gets a chance to set running to false? How does your caller then know that the coroutine does not exist anymore and not potentially breadlock itself? So your caller could be blocked waiting for a news on cout, but it gets nothing. So yeah, it panics. There's no writes to caller, and your caller is blocked. What you can do is simply just whenever your coroutine panics, just propagate this panic up to your caller, and you can just write into cout, which is what the caller is waiting on. Write into cout that I have panicked and don't exist anymore, so don't try to resume this particular coroutine. And this can be implemented using this defer func. So how defer works, if you don't know, is that it just runs at the end of your function. So after everything is stopped running, your defer runs, and all it's doing is that checking if running is set to true. Now, if your control has reached your defer function and running was not set to false, which basically means that something went wrong over here in this grayed out portion, which means that your callee possibly panicked. So if it reaches the def function and running is set to true, you know that something bad happened. Set running to false, and into cout, which your resume is waiting to read from, just write the message panic. And now your resume function can handle this panic however it wants to. It can return in this case, but you can do whatever you want to with this panic. So you've solved that deadlock situation. Finally, we need some way to tell the coroutine or your callee that it's no longer needed. And that could happen because maybe your caller is panicking, or because the caller is simply returning, right? And it's the same thing, but in reverse. Your subroutine just needs to tell your callee, on the channel that it's waiting on, cin, that the parent of this particular function does not exist anymore, and you can stop working as well. So it's just the reverse of what we implemented. So, but what we can do is, write into cin that the caller is canceling. Just propagate this cancel call to your callee, which once it receives the cancel, it can write into cout that I acknowledge that the caller is cancelled, and the caller knows that successfully cancelled its coroutine before stopping itself. So you have your cancel function over here, and all it's doing, it's writing into cin a special kind of a panic, which is in this case this error cancelled, into cin, which your yield function can then handle. So if in your yield function, if it gets a panic on cin, it knows that the caller or the invoker of this particular coroutine does not exist anymore, and I can go ahead and cancel myself. You can pause and look at a bunch of other things that's happening over here. So finally, what are the runtime changes that can be made, right? That's the interesting bit. So far, we have defined coroutines using pure Go. Rust builds on this use of an optimized runtime implementation, and what he did was initially collecting some performance data, and he saw that this Coro implementation that we've been describing took approximately 190 nanoseconds per switch, which lies in the realm of what a regular Go routine switch takes, at a few hundred nanoseconds. He changes one thing first. He marks in the compiler, he marks this resume and yield, these send receive pairs, as a single operation. So now these aren't two separate operations that need to be scheduled by the Go scheduler. It's one single atomic operation. So you are completely bypassing the scheduler, and you can just directly jump between coroutines instead of waiting for it to be scheduled, your resume to be scheduled and your yield to be scheduled. You're bypassing the scheduler entirely. So this implementation actually required just 118 nanoseconds, which was 38% faster from our current implementation. Then he talks about adding a direct coroutine switch to the runtime. So you're avoiding channels entirely. Channels are pretty heavyweight in the sense that they are pretty general purpose. They're intended to do a bunch of things, not just a coroutine switch mechanism. So instead, you can have a direct coroutine switch in runtime. And that implementation actually just took 20 nanoseconds per switch, which is 10 times faster than the original channel implementation. So, if this ends up becoming native to Go, it would be really interesting to see how developers use this really, super fast implementation in Go in various creative ways, and, to see how it changes the concurrency landscape that Go has sort of spearheaded. We covered quite a bit, and thanks for making it here. We're able to show that having a full coroutine facility in Go makes it even more powerful for implementing very robust generalized concurrency patterns. We covered the basics of coroutines, its history, why it's not as prolific, the problems with it, why it's not present in a lot of mainstream languages. We showed why we care about full coroutines, what full coroutines are as different classifications, why we need to have coroutines in Go and how they differ from Go routines and how they would differ from existing implementations in other languages like Python and Kotlin. We then implemented a coroutine API using existing Go definitions, and we built on it to make it a little more robust. We showed what runtime changes can be made to make this implementation even more efficient. Finally, these are the references. I highly recommend going through all of these articles and videos. They're super interesting and quick reads, and definitely go through Coroutine for Go by Russ Cox. That's where a lot of this talk was taken from. Finally, the artwork is by Rene French, 1010, Quasilite. Check out their artwork, some really interesting things. And yeah, thank you. Thanks a lot.